There are a total of n classes labeled with the English alphabet, A, B, C, and so on. Some classes are dependent on other classes for compilation. For example, if class B extends A, then B has a dependency on A, and therefore A must be compiled before B. So we have a list of dependency pairs, find the order in which classes should be compiled. And I think this example should make things clear. So we have this. This is the parent of this. So this needs to happen before this. This needs to happen before this, and so on. This needs to happen before this. And it's represented by this graph. So these are the possible output, like ways that they can be compiled. Same here. This is the parent of this, and this is what it looks like, and this is what we're going to output, an array of strings. And for the solution, this is the solution for this same graph, right? We are going to first do a bunch of things, and I think it's worth looking at the code at this point, to be honest. So this is the function. We pass in the dependencies of, again, parent and child, right? Or child and parent. Child on the left, parent on the right. And an array of tuples. And then this is what we're going to return, the sorted order we're going to return. And this is an adjacency list. And you're going to, if you're not familiar with the term, you'll see what it is, right, as we proceed. And there are different ways to represent this, but we're going to use like a hash map. A hash map where you have a key of a class and an array of its children. So A and all its children. A is a key. Then the value is the children of A in an array. And that's an adjacency list, right? And there's a way of representing a graph. And one way of representing a graph. I think the intro video might have shown the other way, but I could be wrong. Which is another way to represent a graph is a 2D array. Moving on, we're going to have the in degree, which in this case is key value pairs of that tell you how many edges come into a particular vertex or node. And so we're going to initialize the graph and the in degree here. And we have loop through the dependencies. And then for each one, we get the parents. Remember, the parent's on the right, the child's on the left. And construct our adjacency list for parent and child, right? Initialize them to empty arrays. And these arrays are going to hold the children of each vertex, each node. And then the in degree. So basically how many edges are coming in to each node, well, for parent and child. Set it to 0. And so, for instance, you look at A here, no edges coming into it, only things are coming out of it. So we call that a source. And then anything that doesn't have anything coming out of it, but only things coming in, fun fact, not super useful for this example, we call a sink. So E is a sink. And so when we set things up, we come away with this. This is our in degree hash map. So we have the different vertices and nodes, and we have the in degrees. So this says how many edges are coming in. So you can see from here that A has no edge coming into it. And so we set that to 0. And so on. Every other C has 1 coming in, B has 1 coming in, E has 2 coming in. Okay, so we're going to get to this source very shortly. And that source is a queue. But first of all, we look through here and see that, okay, if there's nothing in the graph, return an empty array, which does make sense. But then we populate, this is where we populate the in degree and the graph. Okay, so we've compiled our graph essentially, right? For every parent, we push a child into its array, and we increment the in degree of every single child we see. Set that to +1. I'll be incremented by 1. And that's how we compile this. Basically, that's how this was created. And then the source is a queue, and the queue is going to be a queue that contains everything that sources is going to contain every single source in the array. And we're going to create those sources systematically, one by one. And how are we going to do that? First of all, we're going to put everything that has a in degree of 0, right? So every source, we're going to put it inside a source queue and queue it. And then later, we're going to process every single node, every single source. Basically, you can say a source, or you can also be described as a node with an in degree of 0. I'm repeating things over and over again because that's how things stick. And so while there's something in the queue, right, pop it, get it out there, put it in the sorted order, what we're going to return. And then decrement the in degree, right? In our in degree hash map, right? In this table here, decrement the in degree of all its children. So remember, we have all its children in the adjacency list. So we loop through them in here with a for each, and then we decrement the child, because again, we've pop the parent. We've removed the parent from it. It's kind of like disconnecting A from here. So we need to reduce the in degrees for B and C. And that's what we do. And then we pop them in there because now they become sources. And the sources are a queue holds individual sources. So A is going to move from A to then hold B and C, as you can see here. And again, we removed A right from the graph. And so once we've done that a couple of times up until when the source ends up being 0 for real, right? There's nothing else to do. So that's the while loop working, basically, like getting rid of things and making things work. And then when we're done, we check, oh, is there a match? Because if there's a match, then there's no cycle in the array. Remember, with tuple sort, there has to be no cycle in the array. And then once we're done with that, we can return the sorted order. C'est fini. That is all there is to this problem. And for the time complexity, we're dealing with graphs, so we're dealing with vertices and edges. So we have big O of V plus E, where V is the number of vertices and E is the total number of edges in the graph. And the space complexity is the same, right? Because there's a queue with O of V elements in the worst case, and a hash map with in degrees and vertices, which also has O of V. Additionally, the solution creates a graph with O of E edges, where E is the total number of dependencies, contributing to the overall space complexity. And that's all there is to this problem. Thank you. It's similar to a number of LeetCode problems, like course scheduling problem and the like. And that's all. Thank you for watching. Like and subscribe. Feel free to share. Thank you.